Well, good morning, everyone. This is Jim Chastain with EasyPower. Welcome to our Tuesday refresher session. The main purpose of this whole series of weekly webinars is to both refresh and expose people to not only the basic elements in EasyPower, but some of the underemphasized utilities and features that can make our jobs easier in terms of doing the calculations required for engineering studies. This morning is a case in point, and specifically we're going to spend 30 minutes talking about the short circuit options, and most importantly is how dramatically they can affect the energy calculations in arc flash. So welcome to all. I want to start with our first poll question and get some feedback a little bit. First of all, on scenarios, when you're doing working an arc flash study, how frequently or how often do you set up scenarios, and how many might those entail? And scenario manager is actually one of the topics we'll be covering in the next few weeks as well, so I appreciate the feedback. And here's how folks are looking. So I guess that's probably what I expected. So let's look at the second question. And that is regarding the IEEE recommendations for doing calculations. Which of these do you consider whenever you're doing arc flash studies as far as making sure that your results are complete? In some ways I'm kind of taking liberties with the verbiage, but I'll kind of get into what, because there is some confusion, potential confusion factor, both in the way it's presented by both NFPA and IEEE, but in some regards it's a feature in the tools that people don't readily understand. So again, I appreciate your feedback. To be honest, it's more of a kind of a trick question. Here's how people are responding, and I'll get into more details here. It turns out there are several scenarios that are referred to or recommended in the IEEE regulations, and I wouldn't call it written in fine print, but sometimes it's obscured in the way it's referred to in the documentation. So between now, the discussion today, and the discussion when we get into Scenario Manager, we will be covering all of this. So it turns out actually all three of these are part of recommendations that are made in various parts of the documentation. So I apologize if you felt like that, because it was kind of a trick question, so I apologize if I was misleading anybody. And so let's jump into the meat of what I wanted to talk about today. And in essence, when we talk about short circuit options, there's two applications, or two places where we encounter it. One in the global situation, and then secondarily, literally every bus in the one line has the ability to localize or customize the settings for that particular bus. And we're going to talk about each of those because they play an important part in making sure that you get the most accurate representation for your client and for your study. And the way you look at it is you look at the overall project and you decide whether or not the global settings are going to be most useful and require the least amount of exceptions, which you will need to handle on a local bus basis. And frankly, in some cases, the older systems may require a more conservative approach, and a newer facility might be just the opposite, whereas the global might be the way that most of the systems set up, and you don't need the amount of exceptions you would in an older facility. And then likewise, system configurations, there are these recommendations that I was referring to by IEEE. Some of these options or some of these configurations are built into the EasyPower short circuit options, and they can be customized, while others need to be addressed using the scenario manager. So we'll kind of cover each of those in multiple sessions here. All right, so what I'm referring to as far as the global settings are when we're in the short circuit focus, it's the icon right here that says SC options. It opens up a window that looks like this and has a number of tabs along the left horizontal sidebar. And therein is where we'll be addressing each of these, the focus in terms of global options versus local options is on the arc flash hazard tab, and all of these in this particular box are affecting the whole project. And so I'm actually going to go through an individual bus or local bus setting first, and then we'll make the comparison as we jump into the global secondarily. All right, so with that, let's jump into the tools and see how things look. Now, for those of you that have not upgraded to 9.8, I would suggest that that you want to look at or make sure you know that there's a start window available, and it's accessible from virtually anywhere in the EasyPower tools, but it gives you a lot of advantages, and we will get back to this at the tail end of the session because it's a good link to reference material as well. For now, I'm going to be using a file that's in the sample dialog. So if I go into Open One Line, Sample Files, which is in My Documents, EasyPower 9.8, One Line Samples, and we'll look at Smart PDC. Anybody wants to follow along? And what we're seeing here, if we kind of expand this, is a kind of a typical one-line diagram that has a lot of capabilities. And like I say, I'm going to jump into the local settings because after looking at the system, I see that I have two switchgear panels here that have a potential for maybe settings that may be different than my global settings. And frankly, the same is true when we talk about panels or MCCs. So I'm going to open up I'm in Database Edit. I'm going to open up the dialog box for this particular bus. And as I do that, I notice that this is the specification page. For starters, I don't have any rating or bracing information, so that's something that needs to be addressed. I see that my switchgear has been detailed, and the ratings are set up for the individual feeder systems, but I haven't enabled a spreadsheet for this, so I may come back to that in a second. First, I want to start with the arc flash hazard tab. Now, this actually reflects a lot of the information that's on the global short circuit options, the difference being that this are all set up just for this one bus. And as I look at this particular bus, physically go out and look at it, if I open up the cover or open up the panel cover for the switchgear, and I see that this main feeder breaker the main breaker coming into it is in my direct line of sight, and I'm physically exposed to the connecting points, the cables coming into the main breaker. For me to work on this bus, switchgear 2F, to do any hot work, then I cannot count on this breaker trip settings to protect me and thereby reduce the amount of energy that I'm being exposed to in the case of an arc flash. And the reason for that, if you look at the IEEE results, they discovered that once the plasma ball has been initiated, whether we initiate a fault, an arcing fault on the bus side or on the upstream side of this breaker, once that plasma ball has established, it can propagate the source of the arc anywhere within that ball. So if we initiate a fault by dropping a wrench, let's say across a couple phases, as I'm working on the hot switchgear, that plasma ball, if it encompasses this main breaker, it could arc itself at the bare conductors above the breaker. So in that case, the arc flash output for this bus would have to exclude the main in terms of calculations. All right, and so we'll kind of talk about this again, but that's the primary purpose for this this selection. So in this particular case, we realize there's no barrier between the incoming cables and someone working on the hot bus. Now, in more recent equipment or more recent breakers, there are barriers here, in which case I can include it, or if this breaker itself is in a separate cabinet or a separate section where there's a barrier between its upstream connections and the main bus, then we can include it. So, with that said, let's kind of go on for a little bit further. Likewise, if I'm calculating incident energy for this bus, let's kind of just leave this for a second and go farther upstream. Let's say this particular bus, my utility incoming switchgear. We see, as I open up the dialog box, that there's no protective device upstream of this bus. So if I'm looking at my arc flash setup for this bus, I can't very well calculate anything for incident energy. I've kind of got two choices when I look at the short circuit options. Actually, so there's three. Calculated means that it takes the short circuit current and the trip settings for any upstream device. Since there's not one, this is just going to be not show up on my report, and so my client or my factory people may say, well, does that mean I can work on this bus hot or not? So I have two ways to go. I can exclude it, which means it doesn't show up on the report and it doesn't have any calculations for incident energy, which may be perfectly acceptable as long as we never have to open up this panel or work on this bus. Or if I have a reported trip time from the utility company, I can force it to, or rather calculate it based upon the times that they give me. So user-defined times, say it might be 2 cycles or it might be 6 cycles. Let's say it's 2 seconds. So whatever that time is, I can enter it, and I might say this is a utility trip as far as the upstream device. And so based upon that, I'm defining the time, the max time that this energy would be calculated. So let's say that's where we want to go with. Likewise, if I have a bus here, let's say this breaker, this relay, where it was a time-related relay. In this case, if we look at this, the functions in this relay, it's both phase over current and ground over current. So these are dependent upon a certain level. In this case, we have it set up for the momentary current. Then that's what's going to be used in calculating incident energy for this bus downstream. If this were a differential relay or an arc flash relay that had a sensor in this bus or anything downstream, then the arc flash time for this bus would be based upon the delay that this breaker conveyed. And so again, it would be a time setting for the local bus, not for the breaker itself. So in that case, we would come back to calculated and set up user-defined times. And in this case, we would identify the breaker if it were an arc flash relay, for instance, and the function that would be instigating this particular type of time or delay, and then that's what would be used on that particular bus. Now again, these are all so we can see that I need to put something in there before it let me get out of here. These are all on a local basis, and as I set these, they will override what's being calculated as we do the short circuit calculations. So as we fault those buses and look at the incident energy, we can see that we have a calculated version up here based upon the 2-second time. Granted, it's very large, and we don't want to have anybody work here, but that's what we designated as far as the local bus exception. So let's go back and just to look at the difference. So normally, if we don't use that and we say calculate based upon the trip settings, we fault the bus. you can see it doesn't show up, and when we look at our arc flash spreadsheet, you can see that we have no valid upstream device. So it ends up being an exception that we either need to explain or somehow, well, it won't have a label on it either. So in either case, we've got some work to do. Likewise, if we go back to the same local setting and go under arc flash, we may just want to exclude it because nobody ever has to access this gear, in which case when we go back and do a short circuit focus, fault the bus, arrange for arc flash, now our main switchgear A doesn't show up on the listing at all. Okay, now what we've done for each of these is set up let me see what we're doing for and here we can see our relay, bus 2, and so so what we're doing is essentially manipulating the settings for the local settings for main switchgear A, so it'll either show up, not show up, or have specific time settings for the instant energy calculations. So let's kind of go back to the parade rest here. All right, so that's how I handle each of the local buses when I know there's an exception. How I handle the main or global settings is from the short circuit focus page, short circuit options here at the top. And again, I have these 4 tab settings on the left. Control allows me to set up what type of fault we're using. Again, 3-phase balanced fault is the only one that the IEEE model has characterized, and so that's why it's used most of the time for calculations. We can control what the X over R calculations is being conducted, or how it's being conducted. The recommendation is to use ANSI. We're not going to be changing any driving point locations. The equipment duty threshold we're setting at within 10 degrees of the rating, and voltage sensitivity within 30. So these are all the control set points that will set the flags to turn any of the elements red. Text output is all the reports. One-line output, this is what's the units and what's being shown on the one line when we do a fault. And again, our custom global settings are controlled by this particular tab. Now this is kind of where I want to spend the rest of the time. So this is consider the global settings for short circuit options. And the first box gives us by default the IEEE 1584 model that's used for calculating the incident energy. There are other models in the tool, and these are for specific applications in different voltage levels that industry pundits believe there's some inaccuracy, and in most cases it's a more conservative analysis or more conservative calculation than the 1584 model permits. So if you have questions about what part of the voltage spectrum to use a different model, please contact tech support at easypower.com. For the most part, this is anything from 250 volts up to 16,000 or so. Okay, worst case arc flash hazards. Again, this is a description of whether to include the main or exclude the main on any individual bus. And as we do this, this will change radically what the calculations will be. So let's go ahead and apply this. Fault the buses. Let's look at our arc flash calculations and go back to our short circuit options. All right, now we're excluding the main, which means when we calculate the incident energy for switchgear 2A, we see that it's being protected by BL2B. So without the branch on there. It's hard to see, but that's going to be this puppy up here. If we go in and say include the main and apply it, fault our buses again, we see that switchgear 2A is protected by the relay. If we go in and say compare both, include and exclude, in some cases, and frankly this is an indication that that we may have miscoordination, which is the purpose of this particular example, that in some cases the incident energy may change because in most of these upstream protective device is the relay, which is quicker than the downstream bus. So when we come back to our short circuit options, we need to make a decision whether or not to include or exclude the main breaker on a global basis. Likewise, IEEE recommends that we compare the 85% arcing current with 100% arcing current and use whichever is the worst case for incident energy calculations on bus 1,000 volts or less. EasyPower does this automatically, although we can change what these set points are. By default, they're set at 100% and 85%, and this shows up in the arc flash hazard spreadsheet wherever the incident energy calculations are in dark type. That means 100% arcing current was used for the calculations. Whenever the incident energy is in magenta type, then these calculations included the 85% arcing current. And again, this is handled and reported as such, but these can be modified if for some reason we have a policy that's different and we want to look at different points on the trip curve of the protective device. Fourth element in the system has to do with the ability to limit maximum time for calculations based upon the voltage spectrum that we're looking at. So we saw earlier that we could limit each individual bus to a specific time based upon what type of protection was upstream, and this allows us to segregate and do those calculations by voltage. And there's an application note that if you haven't seen it, you should ask for or download. That's called Calculating Arc Flash Solutions for Low Voltage Systems. What that recommends, and it's based upon IEEE testing, is that for 250 volts or less, you can actually get very long trip times if we have low current faults, low magnitude faults, and unrealistically high trip settings or trip reports from the fuse or the relay, the breaker that's upstream. So this allows us to limit the maximum time based upon voltage spectrum, and frequently the testing that IEEE conducted reported that they could not get a arcing fault to sustain beyond 300 milliseconds below 240 volts. So this tool allows us to set the maximum time for those types of faults based upon entering a number here, and depending upon your system and the type of equipment you're using, you may be guard banding by as much as 300% by putting in 1 second as far as a maximum time, or you might even put in less than that if the current's low, because even at 0.6 we have 100%, you see 100% guard band as far as that particular safety factor on a bus that's less than 250 volts. Likewise, for higher voltage settings, it may be, the recommendation is potentially use a maximum of 2 seconds based upon the ability for an operator to be able to remove themselves from the arc. I personally don't like to set up this until I know what the incident energies are around the plant, and then potentially may make that change to 2 seconds if it's warranted, more on a local basis rather than on a general basis. But that comes down to your judgment and your assessment of the particular specifics of your system. Okay, likewise, other elements that are part of my customs options is the ability to use momentary interrupting 30-cycler integrated current. Momentary is the maximum current that happens in the first half cycle of a fault. Interrupting is the maximum current that happens in the first, during the succeeding 5 cycles. And then 30 cycle will be the current that the fault would essentially show at the 30 cycle point. Now, there is a potential for a very long fault that we could have exceedingly high incident energy if we see a fault that lasts for, say, 20, 30, or 40 cycles. If we use the momentary current for all of that time, we'd end up with a very high incident energy. So that's the reason for having these other current settings available. EasyPower has also included this 4th setting called integrated, although it's not included or recognized by the IEEE model or standard. It actually produces a more accurate result, because if we have a long trip setting, a long fault, for the first half cycle, the momentary current will be used in the calculations. For the next 5 cycles, the interrupting current will be used in the calculation. And for anything beyond that, the 30 cycle will be used, and that's all compensated for or comprehended in the integrated model. So it ends up being a more accurate result, and sometimes can give you some insight into how dangerous the situation is. Then a couple of these other parts of this options end up being very useful if we have a particular incident energy problem where the work that needs to be done, the distance that the worker is from the arc or from the bus that has a potential for the arc, can be mitigated or modified if they use a breaker bar with an extension on it or some kind of tools that give them a little bit more distance to the bus. By default, EasyPower is set up for 480 volts, let's say, this voltage range, 300 volts to 750 volts. The incident energy threshold is set at 4 calories per square centimeter. It's a default working distance of 18, 24, and 36. These numbers are all set and applied and available within the arc flash hazard spreadsheet by just clicking on this little positive sign beside the bus. Now, if we see that, all right, at a working distance of 18 inches, we see a 28.1 incident energy, which is too high. And let's say we have arc rated PPE that is good down to 20 calories, to 25 calories. The question is, where is the 25 calorie limit, and how far away does the operator need to be able to make it a safe working condition for that? And that's where we're allowed, through the short circuit options, to create an intermediate set point. And so we're looking at 450 volts, and we want to look at something between 18 and 24 inches. So let's go ahead and say, show me what the incident energy calculation is at 20 inches. So as we expand that, so now we can see 18-inch incident energy, 24-inch incident energy, and 20-inch incident energy, at which point 25-calorie equipment, PPE, would be adequate to protect the worker and allow us to work if we have the ability to move the worker back or if his actual working distance is at 20 inches. So this gives us the ability, technically it doesn't change the incident energy calculations, but it does change what we're going to be putting on the label and what the safe working conditions might be for somebody working on that bus. So again, that's part of the short circuit options mode, and each of these settings will affect not only what's being calculated and how that calculation is being reported, but how that information shows up on the arc flash hazard spreadsheet and then ultimately on our label. Now, I noticed by looking at this, this is obviously an older model, and I've just had to reinstall. I had to update to Windows 10, so I had to reinstall my Windows and my EasyPower. But I noticed that I'm showing what I would consider a violation of NFPA 70E 2015 by showing the HRC category, which I do not want to show on my label. The ability to control that is an extension of the short circuit options advanced button, which allows me to either show the PPE or not, and then utilize NFPA 70E H3B table, which is the recommendation for 2015 version. And as I do that, you'll notice it takes off my PPE categories, and now we're able to produce a label that's going to be compliant. Okay, so what have we covered? We've talked about the ability to set global options, the ability to override the calculation time at a local bus, to include or exclude the main for all or each bus in the system, and how that affects my incident energy calculations. Now, it also brings up the discussion like, well, if we have the ability to put up a temporary boundary, if for some reason we need to do work on this bus, and this high number is by virtue of the fact that we excluded the main breaker, does it make sense to consider what constructing a temporary boundary would do? Again, those are discussions my maintenance team would have once we looked at the results and we're looking at what the procedures need to be for work in a given bus. So all that is part of seeing more the danger and the contributing factors to arc flash incident energy calculation. All right, so that covers the global settings, that covers the local settings, and that pretty much covers what I was trying to deal with. Appreciate everyone attending. Have a good rest of your day, and we will talk to you all next week.